In this video, we are talking about the application of gradient descent method for the task of logistic regression. In our previous video, we are talking about logistic regression, which is used to effectively perform binary classification of data, and it is based on the sigmoid function, which here is shown as depending on the two parameters w and b. W, the weight coefficient, and b, the constant bias. And here, this form of sigmoid function is shown for two possible sets of data. Also, we can show it using slider. Following slider prepared in Python, we see that by changing the parameters b and w, the form of sigmoid function is altered, and we can try to select these parameters to optimally, in some sense, some optimality sense, to approximate our data. So, what criterion should we use, optimality criterion? Of course, as in any classification task, machine learning task, we must have training data, we must have labels for them, and we must have some optimality criterion. And intuitively, we can use a loss function as the loss function, the function of loss. So it should be very low if we have a good approximation of our data, of labels, and it should have a high value, large value, when our approximation is poor. So to select loss function, we can select loss function as is shown at the middle of the slide, according to mean square criterion. Yes, it's possible solution, and the corresponding cost function. Cost function, please take note that cost function is called the averaging of the loss function over the whole training data set. And the cost function will have the following form, which is typical for the mean squares approximation. We must remember that function f here is not a linear function, as shown at the upper part of the slide. It's a sigmoid function depending on w, x, and b. So we can use, of course, this cost function, but it occurs that it's not always convex. So the iterative methods, such as the method of gradient descent, could fail to find the optimal solution. We must select some other loss function. So what could be the possible choice for this function? Again, intuitively we understand that the loss function must tend to be infinity if the difference between y hat and y, between the approximated, predicted, and the true label is large. And it must be close to zero when these values are quite close to each other. To be more specific, if yk, the sample of the label number k, is equal to 1, this loss function should tend to be 0 if y hat is also close to 1. On the opposite, for example, if yk is equal to 0, if our approximation, our prediction, y hat k tends to 0, then also the loss function must be approximately 0. And also it must tend to be infinity when we have the opposite decision. So the loss function must take some high value, large value, when our decision is wrong. And we can see that the following form of loss function is appropriate for this task. For example, when yk is equal to 1, then if we select the loss function is a minus logarithm, inverse logarithm of yk hat, predicted label of y, then let's see, if y hat is equal to 1, the logarithm of 1 is 0, so it's good approximation. And when yk is 0, when the true value of label is 1, we will have multiply minus infinity, we will have plus infinity. So this loss function will produce the value of infinity. So this function, and the same for the opposite case, when y is equal to 0, we select the loss function as minus logarithm, natural logarithm of 1 minus y hat. So we can generalize this to find the loss function in the following form. So minus y multiply logarithm of y minus 1 minus y multiplied by logarithm of 1 minus y. So it's to those of you who are familiar with information theory, this looks much like the entropy, and indeed it has definite similarities, but we will talk about this in more details in the following videos. So we have selected our likelihood function, loss function, and also here I will not go into the details, but we can find the same value of cost function based on some probabilistic interpretation. So by taking the logarithm of likelihood for the whole set of data y, we can come and taking the minus inverse logarithm of this likelihood, we can come to the same formula for the cost function. Again, this formula for the cost function is shown here at the bottom of the slide. And it's very good news that this function is convex. It's convex, and that is why we can apply the method of gradient descent to find its minimum. So let's recall the methodology of method of gradient descent. We have cost function. We must find the values of w and b which minimize this cost function. We start with some initial approximation, and then we are making some small steps. We are incrementing w and b in such a way as to reduce the value of cost function. And we must have some stop criterion, or just to finish the prescribed number of iterations to find our solution. So we must, again, we are having here at the upper part the formula for the cost function. We must, to apply the method of gradient descent, we must calculate its derivatives by partial derivatives by w and by b. We have a very nice property of sigmoid function which can be used to effectively calculate the derivatives of it means the gradient of function j, of our optimality criterion, cost function j, and these formulas are given here below. Also, I want to show you some intuitive interpretation of how are we calculating these derivatives. As we will talk about when we will discuss the neural networks, there is some kind of forward run when we are calculating parameter z, wx plus b, then we are calculating value a, which is sigmoid function of this z, and then we are ready to calculate the loss function. And then we are calculating in the backward direction from the right to the left the corresponding derivatives, which are necessary to apply the method of gradient descent. We are calculating the partial derivatives by a, which is a, recall, is in the second block, it's a sigmoid function of z. Then we have a very compact formula for the partial derivatives of loss function by z. It's equal just to a minus y. And we're using, of course, the chain rule for the calculation of derivatives. And finally, we have expressions for the partial derivatives by w and b, which we are denoting here for the sense of compactness as dw and db. dw is equal to x multiplied dz. dz is a partial derivative of loss function by z, and db is simply equal to dz. So we can very efficiently calculate in this way the gradient of our loss function. And then again, we recall that we are forming cost function by averaging the values of loss function for each training sample. So this is our cost function. And we can apply to it the method of gradient descent, and it can be represented by a very simple symbolical programming language in a cycle. When we are going through our training data, the number of training samples is m, and at each step we're computing z, then as a weighted sum of wx plus b. Then we are computing the a, which is the value of corresponding sigmoid function. Then we are incrementing our cost function. We are calculating dz, and finally we are updating dw and db. Very compact algorithm, very short algorithm, which can be effectively realized. Of course, we must also here apply some vectorizing, which will make this algorithm even more efficient to be applied on some computational platform. Okay, let's finally consider this example of applicating this gradient descent method for the set of data which we considered in previous video and at the beginning of this video. So this is how the cost function reduces. It descends when with the growth of number of iterations. And here also we can observe how the method of gradient descent gradually converges to the local minimum of the cost function. The 2D plot is shown on the left, and on the right we have a 3D plot, which on the projection to the plane of W and B, we can see that these crosses, which correspond to the values of W and B for different iterations, converge to our desired point of local minimum. So I believe this is all what I wanted to say here. We discussed in this video shortly the application of method of gradient descent for the task of logistic regression, binary logistic regression. Thank you very much for your attention.